Okay, our next speaker is Debakanta Samal from Institute of Physics, Bhubaneswar, and he is going to talk about emergent electronic and magnetic response in antiferromagnet-proximitized strontium iridate and copper-based quasi 2D hybrid perovskites.
Okay. Thank you, Srimanta. Yeah, I'll take it. So first of all, I would like to thank the organizers for giving me to present some of our work. So I will be talking about two aspects here. As I mentioned, I will talk about how antiferromagnetic proximity close to a spin orbit coupled material, that is SrI, gives rise to some emergent topological electron transport. And the second part of the talk, I will talk about a quasi 2D material, that's quasi 2D hybrid perovskite, which are basis to look for the 2D magnetism. So the outline of the talk is the following. When I proximitize an antiferromagnet close to a spin orbit semi-metal, we observe some kind of chiral anomaly, giving rise to a signature that it is a Dirac semi-metal, which is not found in the bare SrI. And this is also because this chiral anomaly is because of there is enhanced phase coherence length, which is because of coincident magnetic impurity scattering. And in the second part of the talk, I will be talking about these quasi 2D magnets. Particularly, I will show that we get completely contrasting magnetism in this kind of copper-based system when you go from one ligand to another ligand. So basically, it is a ligand tunability of this nonlinear magnetism. And I will show that this contrasting magnetism only we can understand when we invoke the concept of nonlinear magnetic structure in this kind of materials. So the first part of the talk is done by PhD scholar Subhadeep Jana, who is now in Israel doing postdoc, and these people are the collaborator for this work. And this second part of the work is being done. We are still working on it by Pujalin Bishwal, who is a participant here. And some of the things we take the theoretical help in the first principle calculation from Ashish and SD Mohanty. They are helping us in understanding some of the data. And yeah, these are the findings. Okay, before I go to iridates, let me introduce the spin orbit interaction, because we know that if you look at from electron frame, so we know that a moving charge particle, when it experiences electrostatic potential, it effectively experiences a magnetic field. This is for a simple cartoon picture from textbook. When if you look at from the electron frame of a reference, then you experience a magnetic field, that's B prime. Similarly, if we are considering a solid where in a itinerant system where the electrons are moving, so they can experience an electric field coming from the crystalline lattice. And that is and generally this atomic spin orbit coupling varies as z to the power 4, where z is your atomic number. And if you look at the spin orbit interaction of various energy interactions that's present in the material, so here we have put this all the interaction energy. If you look at, there are two important energy scales which I will be concerned about, which I will try to bring to your attention. One is you look for the spin orbit interaction energy here. So that is typically less in conventional systems, and compared to other electron interaction or any kind of other kinetic interaction. And if you look at another interaction, which is your epitaxial strain, because we work on thin films and heterostructures, quantum materials. If you look at this epitaxial strain, look at the energy scale in terms of energy, so it is very high. So that means there are certain materials, because why I am introducing this, because this SrI, which I will talk about, it is very difficult to stabilize in the bulk form because it requires very high pressure and high temperature synthesis. But by making thin films, by introducing strain, you can stabilize this SrI in a kind of a perovskite phase, which is a very potential candidate material to realize the topological electron transport. So this epitaxial strain and the spin orbit interaction, these are the two energy scales which is very important in the context of this work. And now this is the very conventional spin orbit interaction which I talked about. But if you look at the various transition metal ions, like when you go from 3D transition metal ion to 4D transition metal or 5D transition metal, we know that as you go from 3D to 5D, the electron wave function, the orbital gets extended, so the Coulomb repulsion decreases. So that is what the Coulomb repulsion decreases when you go from 3D to 5D. But as I mentioned that the spin orbit interaction varies as z to the power 4. So when you have for the high elements, high z elements, the spin orbit interaction increases. So particularly for the 5D transition metal oxide like iridium, osmium, what happens is that in here, generally in doing the physics for 3D, you can trace the spin orbit interaction. It does not matter much. But when you are coming to the do the physics of 5D transition metal oxides, you cannot trace the spin orbit interaction because spin orbit interaction and Coulomb interaction, they kind of compete each other. So, so that because of this interaction, because there is a competition between this Coulomb U and this spin orbit interaction, you can see there are various kind of novel phases that emerges in this kind of spin orbit coupled materials or iridates. So here let me start with one candidate material that is the SR2IRO4. If you look at its 3D counterpart, this is SR2COO4. If you look at the 4D counterpart, it is SR2RHO4, and the 5D counterpart is SR2IRO4. As I mentioned, as you go from 3D to 5D, the orbital wave function, the orbital gets extended. Naturally, naively, one should expect that if SR2CO4 is a metal, SR2IRO4 rather will be more metallic character. But what is seen that this SR2IRO4 is an insulator. And that only we, and this is the data, this resistivity versus temperature. You see, this is SR2IRO4, it shows a strong insulator character. And this can be understood only by introducing the spin orbit interaction, because if you look at the there is a J effective state comes into picture when you introduce the spin orbit interaction, and when there is a J effective state here, and when you switch a little interaction, there is a gap forming between J effective half and this is lower Hubbard band and this is upper Hubbard band, and that gives rise to an insulating character. But so this is where there is a competition between the spin orbit interaction and Coulomb U that opens up a gap, giving rise to SR2IRO4, an insulator, and this is named as the spin orbit mod insulator. So there are many examples here. So this is a phase diagram where this is the y-axis, this is u by t, and this is lambda by t. So depending upon the strength of this lambda by t and u by t, and you can see in this region, particularly where lambda is more, spin orbit interaction is more, and u and lambda, they are kind of comparable. That is particular, mostly this iridates compound. You will see the emergent of various novel phases, starting from various topological metallic phases like wild sim metal, axial insulator, and as I mentioned for SR2IRO4, spin orbit coupled Mott insulator, and there are various other phases, exotic phases you can see when this U and lambda are comparable. So this is in particularly this iridates like the pyrochloride iridates, and there was a proposal in 2014 that if you this kind of pyrochloride iridates, if you grow along 111 direction, and they will show various this topological phases like wild semi-metallic phases. This is the phase diagram as a function of U, and in recent days there have been many works where if you grow these iridates along 111 direction, you can realize some of the topological phases. So what I will be talking about not these iridates but this SrIRO3. So SrIRO3, if you compare with the SR2IRO4 that I told. So this is your SR2IRO4, and this is known as, if you go from SR2IRO4 to SrIRO3, this is known as the Rudolfson-Popper seed phase, RP phase, and here there is kind of n equal to 1, and here n equal to 2, and perovskite means n equal to 3. So naively, one should understand, or one should expect that if SR2IRO4 is an insulator where there is a gap between J effective half bands, so when you are increasing the dimensionality, when you are growing from n equal to 1 to n equal to 2, because when you increase the dimensionality, the bandwidth will increase, and there is an increase in bandwidth. This is J effective 3 by 2, and there is an overlap here. And when you go to n equal to infinity, so one would expect that this SrIRO3 will be metal because there will be overlapping of J effective 3 by 2 and J effective half bands, because of the reason that I told, because of the dimensionality, that they increase in the dimensionality. But what has been found, as I mentioned, to get this SrIRO3 perovskite phase, so you can only grow it in thin film form. So either you can grow it in at extreme condition by temperature and high temperature and pressure, or you can introduce strain so that you stabilize. Otherwise, the bulk phase always goes to this monoclinic phase, which does not show any much interesting properties. But you can grow this by following the epitaxy method, and you can grade this perovskite phase, and this perovskite phase is supposed to give rise to various topological phases. So as I mentioned, one should expect from the previous slide, as I mentioned, depending upon the dimensionality, one should expect it should be metallic. But look at the data here. So it has been found that SrIRO3 is not metallic, rather it is a semi-metallic in nature. So, and there have been calculations which tells that it's not only semi-metallic, but it is a Dirac semi-metal. Look, here is the band structure calculation. Here that is, you see, this shows that this is a magnetic metal when alpha is equal to 0, and when you consider alpha equal to 1.5, this is a scaling factor in the Hamiltonian. So you see there is a band crossing here occurring at U, the point in the brilliant zone, and this is the point which gives this is a band crossing, and it is a signature of this is like a Dirac semi-metallic nature. And when you increase more alpha value to more, it again becomes kind of insulator. This is the insulator. So this is the kind of, it was predicted in 2012 that this SrIRO3 is not only semi-metal, but it will be Dirac semi-metal. So far what has been known on SrIRO3, there have been some photoemission studies which show that this is a narrow band semi-metal with a linear dispersion. But so far what is, though the RPS data shows that there is a linear dispersion, there is an electronic band which has linear dispersion, but from transport data, there has not been any evidence of clear-cut evidence of this Dirac nature of fermions existing in this material. So what I want to show you in this talk is that, I'm the first part of the talk, that by proximatizing SrIRO3 with an antiferromagnet, we see that there is an emergence of, from transport studies, we see there is an emergence of the characteristic of topological electron transport. So before I go, so where do we get motivated? Why do we want to proximatize SrIRO3 to an antiferromagnet? So this motivation came from an early work where they were interested to study copper, by simple copper. They are growing copper on a copper oxide, where copper oxide is a Mott insulator. So they are growing copper on copper oxide. And in another case, they are growing copper on a band insulator. They are growing, in one case, they are growing on copper oxide. Another case, they are growing on MgO, which is a band insulator. Now look at the magnetoconductance data. They see a very clear signature of a weak anti-localization effect here when copper is grown on copper oxide. Which is, but when copper you grow on MgO and band insulator, this feature goes away. And they modeled this based on the formalism of weak anti-localization effect, and they found that the spin flip scattering time that is kind of anomalously large when the copper is grown on antiferromagnetic insulator as compared to when this copper is grown on a band insulator. And this number is really large. And the idea at that time, because it was not really understood in 2011, the idea they postulated that when you bring a Mott insulator close to a metal, there would be a, because of this proximity, because when you are bringing, because we know that the proximity effect very much reveals when you talk about a normal metal and a superconductor. But when you bring a Mott insulator to a metal, I do not think much will happen from proximity except some charge transfer. But what they find surprisingly is that there is a polarization of antiferromagnetic polarization that happens inside the metal, inside the copper. And because there is a polarization of here, so there is an interaction going on between these impurity spins, whatever is present in the material, there is an interaction going on between the black one, that is your impurity spin, between the polarized spins. And this, so the spin flip scattering decreases because it costs some energy. When only you can raise the temperature, so then only there could be spin flip scattering. But since there is an interaction between the black spin and the localized spin, polarized spins of copper, so it is energetically not favorable to have this spin flip scattering. But in case of when you are growing copper on this band insulator, not such kind of scenario happens. So because of that, what they find is that the spin flip scattering anomalously increases when you just grow a metal on top of an antiferromagnetic insulator. So the idea was more clear in 2015. A more microscopic picture came into picture. So this is, they talk about the spin envelope-like reflection. That means we all know this is envelope reflection. When you bring a normal metal in a superconductor, when you inject an electron whose energy is less than the superconducting gap, either it will get reflected or it will form a high energy intermediate state, and finally a Cooper pair will be created in the superconductor state and a hole will get reflected. This is what we all know in the context of superconductor normal metal junctions. But when you bring a normal metal close to a Mott insulator, so similar kind of situation happens. What happens, either the spin will get reflected without any spin flip scattering, or what happens, so this will form an intermediate state, and finally what will happen, there will be a spin flip, there will be this spin will get spin flip and it will get reflected, and there will be a change in the delta Sz, the magnetization in the Mott insulator side will increase by delta Sz equal to 1. So this was the and because of this, the polarization, spin polarization occurring in metallic side is the natural outcome of this spin envelope-like reflection. So this motivated us to look into SrI-RO3. What happens, because in a copper, they see a very different response when they just put copper on top of an antiferromagnetic insulator. So this motivated us to look into this SrI-RO3. As I mentioned, there was no clear-cut transport from that it shows that it is a Dirac-like system. So we put SrI-RO3 on SrCO2. So SrCO2 is an antiferromagnetic insulator, and we also grew a test sample without putting any antiferromagnetic in between. And this SrCO2, these were some of my earlier work where it is an antiferromagnetic insulator, and we had looked into to see its antiferromagnetism, because you cannot do any standard magnetic measurement. It's very difficult on thin film because it is an antiferromagnet. So you can do the Rix measurement, actually resonant inelastic scattering. You can look at this magnon dispersion, and this shows that this is really an antiferromagnet. So we looked into this system, these two systems, and this is what we did. We grow, these are the general things. We grow these bilayers by pulse laser deposition, reed assisted pulse laser deposition. I'll not get into this more. So here what we do, this is what SrI-RO3 is grown on SrTiO3, and here SrI-RO3 is grown under a layer. There is a layer which is antiferromagnet. But here we are growing a perovskite on perovskite. But here we are growing a perovskite on SrCO2, which is known as the infinite layer. And because the electronic property of SrI-RO3 is very much prone to distortion. To really know whatever the things that we are seeing from our transport, it's not because of distortion. So look into the reciprocal space mapping actually to look at whether there is some distortion or not. So we see that along all the four directions of 103, we see that Qx and Qy values are kind of similar, and similar is the case for when it is grown on the top of SrCO2. So in both cases, we do not see much distortion. Now we look at the resistivity plot. This is for the bilayer, and this is for the SrI-RO3 Bayer. So there is an upturn, and this upturn follows a logarithmic temporal dependence, which could be due to weak antilocalization. There could be some correlation. And this carrier concentration is for both layers come around 10 to the power 19. That is what we expect because it is a semi-metal. And now we looked into, to really look at the scattering rates, we looked into this magnetic conductance, and we used the well-developed formalism of this weak antilocalization. And what we do here is that we calculated the characteristic magnetic fields, this B phi and B SO, and B phi and B SO are related with the characteristic length scale like this. And we used this HLN equation. And what we find is that this is the B phi, I'm talking about now first B phi. B phi increases, this is what increases as you increase the temperature, because B phi is related with L phi by this relation. So as you increase the temperature, so this is B phi increases. And from this B phi, you can calculate that this L phi for the bare SiO is roughly 22 nanometer at 2 Kelvin. But in case of this bilayer, when you are putting strontium iridate on top of an antiferromagnetic insulator, the alpha is increasing. So that is the kind of scenario we see where they were looking at the spin flip scattering time was anomalously increasing. Here we see that the alpha is increasing compared to the bare SRI or O3. So possibly what we are talking about there, that the quenching of magnetic impurity scattering, and that is what is possible happening. That is why the alpha is increasing. But if you look at the BSO for both the things, so BSO generally, typically does not show a temperature variation. But what we see, there is a variation of BSO with temperature, and this was kind of intriguing, a large variation of BSO for the bilayer, where your SrI-O3 is grown on SrCO2. So this was kind of little bit intriguing. So we wanted to try to understand it, what could be the mechanism. So we looked into, because SrI-O3, it does not break the inversion symmetry. So we looked into the kind of spin relaxation mechanism. And since it does not break the inversion symmetry, we thought this the EY type of spin orbit scattering playing a dominant role here. And for EY type spin orbit scattering, the scattering rate is given by this. So from this here, so where tau is the momentum relaxation time. But we came across a paper which was based on the Raman spectroscopy studied, and they found that the SrI-O3 is a strange semi-metal. It has strange semi-metal dynamics. And they got it that the electronic continuum extends even up to 1000 centimeter, roughly 125 milli-electron volt, very similar to some of the parrot compound of high T superconductivity. So, I mean, there are some compound of these cuprates. So, once we know that this is your, this is the strange semi-metal dynamics, and we know how the scattering rate changes when you go from a Fermi liquid where it is T-square dependence, and you go to a non-Fermi liquid where you have the quasi-particles have some long-range interaction between quasi-particles, and if the interaction is not that strong enough, so you will see that it will show a logarithmic behavior. So this is what is for the kind of the marginal Fermi liquid or strange semi-metal, the scattering rate varies like this. So once you get this scattering rate, this kind of dependence, when I put this tau E, whether momentum relaxation time, we see that we are able to account for the unusual variation of a BSO with a temperature. And as I mentioned, generally when this marginal Fermi liquid behavior, they are very prone close to the border of antiferromagnetism. And here we are putting an antiferromagnet proximity to this SrI-O3, we see that the variation is more that kind of enhances the marginal Fermi liquid behavior. Then we looked into really the longitudinal magnetoconductance, and here we see a sharp difference. When you see this bilayer, we see a positive magnetoconductance, and of course this is measured in B parallel to I because we are looking at the chiral anomaly. And but for the only SrI-O3, you see they are completely contrast. One is positive, one is negative. So we try to understand this based on the formalism of this chiral anomaly that is generally used in the context of topological materials that shows the positive magnetoconductance. So what is it about? So this is about if you have a Dirac semi-metal, when you apply magnetic field, the Dirac node breaks into two wild nodes with having different chirality. So this is what you apply magnetic field, you break the Dirac node into two wild nodes with different chirality, and now when we apply electric field, what happens? One of the node will get populated compared to other. And because of that, you will have some axial current. And this axial current is given by, or this call it as chiral current, and this chiral current follows like this, it follows like quadratic dependence of the applied magnetic field. And the population, the chiral population here, that varies as the applied electric field, and tau is your chiral relaxation time. Now you see this is the data where we try to fit it with this expression. This is coming from your chiral anomaly, and of course there is a term coming from this localization effect, and we see that this part matches well with this expression. And if you look at the temperature dependence of this part that varies as T to the power minus 2, that is what expressed here, this C double that varies as T to the power minus 2. And this tells that a contrasting difference between a bare SrI or O3 and when you are sandwiching with an antiferromagnet, because we see and this is because of, and this tells that there is a topological electron transport. But the point is why? Because what we understand so far is that when we are putting an antiferromagnet, your tau A, the chiral relaxation time increases because the impurity scattering is decreased. And once impurity scattering is decreased, the chiral relaxation time increases. So because of the chiral relaxation time increases, you get a more contribution to this chiral anomaly conductivity when you have antiferromagnet. But if you have a bare SrI or O3, the chiral relaxation time this is not the case in case of bilayer. So we see the trivial magnetoconductance. If anybody is interested, they can go through. This was last year. So summary, what I wanted to tell you that the antiferromagnetic proximity effect paves an avenue to preserve the non-trivial quantum phenomena in complex materials by circumventing the detrimental effect of unintended magnetic impurity scattering. Because any material, there could be some ppmm level magnetic impurity, and that could also affect very much your quantum transport. And this method, by just sandwiching an antiferromagnet, it will be possibly an effective way to control undesired spin relaxation by magnetic impurity scattering in the field of spintronics. So this would be my first part of the talk. Then I will go to second part of the talk, where I will be talking about, I will change the gear, but in the first part I told how to engineer a spin-orbital coupled material by proximatizing it to an antiferromagnet. Here I will talk about how we can engineer, how we can get emergent magnetism by changing the ligand atoms in this kind of a quasi-2D magnetism. So before that, one slide, this is a very general slide people talk about when they talk about this 2D magnetism. And we know that according to Mormin-Wagner theorem, whatever it tells that the spontaneous symmetry cannot be broken at a finite temperature for 2D Heisenberg system with short range interaction. But this does not consider the anisotropy and long range interaction like Doppler interaction. And there have been many systems where people see the transition, that is spontaneous symmetry breaking, even at monolayer, and this could be due to various kind of anisotropy present in the system. But to realize a 2D system, you need a quasi-2D system, because the basis for 2D system, 2D magnetism is a quasi-2D material. So these quasi-2D magnets, where the magnetic interaction are strong within the plane, and you have a very weak interplanar interaction. It is not that only the van der Waals materials are quasi-2D. The quasi-2D materials, many of the cuprates are also quasi-2D, because the out-of-plane interaction in cuprates is much less compared to your intraplane interaction. And there have been many materials which have been studied earlier, which has kind of the quasi-2D magnets. So what I'll be talking about here is a quasi-2D Heisenberg magnet. So how does the ordering happens in a quasi-2D Heisenberg's magnet? So this is what we understand. For a quasi-2D Heisenberg magnet, the 2D magnetic correlation exists in each layer at higher temperature. And as you are cooling the quasi-2D system, upon cooling, the correlation length grows exponentially with 1 by T, so that there will be an interplanar interaction with an effective 3D long-range ordering happens as you cool down the system. And basically, this the 3D ordering in this kind of a quasi-2D system, it very much depends upon the interlayer coupling and the anisotropy present in the system. So what we'll be talking about, not the van der Waals material, but this quasi-2D organic inorganic hybrids, they are a family of materials which are quasi-2D. So these are the kind of these systems are like this. You have transition metal ion sitting here, and these ligands, like instead of oxides, here you have chlorine and bromine. And these are the organic layers, and the organic layer spacing is too large, because when the spacing, because you know that the exchange interaction kind of dies even at 1 nanometer. But here the spacing can vary from roughly 1 nanometer to 2 nanometer. And that is why people find the interplane interaction J prime by J, the intraplane interaction is roughly order of 10 to the power minus 2 to 10 to the power minus 6, depending upon the spatial layer, the length of the spatial layer. And you can in fact tailor this spatial layer. Here you can see they've tailored this spatial layer. In one case they find roughly 18 angstrom, another case they got it around 10 angstrom, so that depending upon this spatial layer, your magnetic property completely changes. It shows a ferromagnetic, but here you see there is a downfall in magnetization. But I will be talking, and as I mentioned, this kind of systems are where the magnetic ion it can be these transition metal based systems. But what I will be talking about is copper based system, because the copper based system are more interesting because of two reasons. So they show this orbital ordering, because if you look into the physics of cuprates, because copper 2 plus it is a D9 system, so all the physics happens in the dx square y square plane. But what you find here, because the CuO6 octahedra is elongated along C axis, so you find the whole resides in the dx square y square orbital, so everything happens in this plane. But in this kind of systems, what happens, the elongation, the distortion happens in the plane, so that you get kind of the orbital ordering. You can see one long and short bonds, they lie in the plane. So because of that, you have a orbital ordering like dx square minus z square and dy square minus z square. So unlike the parent compound for high-test cuprates, which are mostly antiferromagnets, because of the orbital ordering, this copper-based system, particularly in this kind of materials, you find them, they are to be ferromagnetism. So because of their ferromagnetic character and the orbital ordering, this copper-based organic and inorganic hybrids, they have taken the attention for some time. And in fact, there have been works where they find that there is a cross-type orbital ordering based on X-ray absorption spectroscopy. They show that in fact there is a cross-type orbital ordering where there is a x square minus z square and y square minus z square. The whole lies in x square minus z square and y square minus z square. So motivated by this work, we tried to grow the single crystals of two new materials belonging to this family, where in one case the ligand is chlorine, in another case the ligand is bromine. And these are the kind of structural, I will not get into this, but one point I want to make you to point out here is the following. As you are going from chlorine to bromine, because bromine is bigger, larger ion, so the copper-copper distance increases. So you see here you are going from 5.33 to 5.52. Now this is one of the busy slide I would tell whatever time I have to show you, because if you consider this chlorine case, you see, first of all, I want to tell you that here the TC in case of chlorine, the TC is roughly around 7K. But if when you go to bromine, the TC is around roughly around, you can find around 12 Kelvin. But as I mentioned, the copper-copper distance increases. Because when you go from chlorine to bromine, the copper-copper distance increases. Naturally, when copper-copper distance increases, so the J should decrease. So naively one should think of that in bromine case, the TC should be smaller. But here we get the TC is larger. So because there is a larger differential, because bromine is bigger ion, so the orbital overlapping is more, that's why we get a larger TC here. But the important point is you see here, in the chlorine case, the magnetization, if you look at the in-plane magnetization, that shows a ferromagnetic-like behavior. You see, you expect 1 mu B, here we are getting roughly 0.8 mu B at application of a 10 volt state. But if you do the measurement in out of plane direction, you see there is a downfall. So reminiscing you like, could it be an antiferromagnetic transition? But it is not the case. As I go along, I'll tell you. But if you look at the bromine case, you see in the out of plane direction, though it shows a ferromagnetic-like behavior, but look at the number, the mu B, if you calculate the mu B per copper, it is very small. It is even less than 0.15. In one case, you are getting a complete close to 1 mu B that is expected for copper 2 plus. But in another case, though looks wise it shows a ferromagnetic-like behavior, but if you look at the magnitude, it is too small. And you can whatever the magnetization versus temperature, that is validated from this magnetization versus magnetic field. In one you see a ferromagnetic-like thing, in another downfall you see a very hard axis kind of thing. So for the similar thing happens for the bromine. So so what I'm trying to understand is that why does this change in the magnetization changes when you change chlorine bromine? Then we look at what could the dominant ferromagnetic interaction. In both the cases, does not matter whether you in plane, whether out of plane, whether chlorine and bromine, because I told you these are the quasi-2D Heisenberg systems. So in every cases we see there is a positive theta C double, and because this tells that the underlying interaction is ferromagnetic. If the underlying interaction is ferromagnetic, then why there should be a downfall in magnetization along the out of plane directions? And to calculate the estimate the J, because these are the 2D Heisenberg systems and these are well studied, and you can use the expansion method to really estimate from the susceptibility. You can, because the first term is basically your Curie, but you can contain this expansion terms here, and you can calculate the J, and these are the fitting for two compounds. In one case we get J21 and another 34. So this is what from our experiment, if you convert it to milli-electron volt, it comes from the chlorine 1.8 MeV. This is roughly 2.93. And we wanted to check with the calculation, theoretical calculation, which was done by our collaborators. So this also comes like 1.94, 3.12. And if you calculate the J2, next nearest neighbor interaction, that was coming to ferromagnetism. So in both the cases, and we calculated that the anisotropy remains in most cases in the plane. So if anisotropy remains in both the cases in the plane, so both these systems should show similar kind of behavior, but it is not the case. So could it be that it could be due to some non-collinear structure that is happening, non-collinear magnetism that is happening in this material? So I looked into calculating this DMI, but these molecules are very big, because in one unit cell you will see many atoms. So it is very difficult. I don't know the theory. I can tell how difficult it is, but what I understood is that it is difficult. So what we did is that we used some of the chirality of DMI to calculate the DMI present in our system. Basically what you do a clockwise rotation, you do an anti-clockwise rotation, and this D is the kind of the difference between these two. And we did this calculation. This is the clockwise helix, this is anti-clockwise helix, and these are the numbers for a representative. This for the chlorine system, when you are doing along the C-axis, and you do clockwise and do anti-clockwise, and these are the DNN, which is calculated. These are the nearest neighbor, this D. If you look at the total calculation for the chlorine, we get a sizable D of 0.026 when our spin spiral is along C-axis. And for the bromine case, we get two sizable D when spin spiral along B and spin spiral along C. So what does it do? This is a D along B direction, So what will happen if your spins are in the BC plane, and as I told, these are quasi-2D magnetism, it will try to tilt towards the AC plane, because wherever the D vector, so it will cant the spins to a perpendicular plane. So this is what I have shown a little canting here because of this. And if you have an out of plane, if you have an out of plane D, what will happen if this is an out of plane D? It will try to cant into the BC plane. So this is how the in plane D and out of plane D will affect the spin direction. Now based on this, what we found, we proposed, because it is very difficult to do any neutron diffraction measurement and to test really whether it is the spin structure, some automatic spin dynamics has to be, simulation has to be done. So, but from naively we can understand from these numbers that your J1 is roughly 1.94 milli-electron volt, and this is your anisotropy, and this is your dB. So though there is a dB which will try to cant, but your anisotropy is equivalent to that. So it cannot cant very way from the plane. So there will be a little canting for this one, for the chlorine sample, because these two compete with each other. The anisotropy will not allow to deviate much from the plane. But when you go to the bromine compound, so you see here, the out of plane D vector is much larger than your anisotropy. You can actually you can do a spiral like this in the BC plane. But on the top of that, it is not only out of plane, you have an in plane also, this one, and which is kind of comparable. So because of this, you will have not only a spiral, you have a conical spiral spin structure. To look more into it, we did the AC susceptibility measurement. You see, when you are applying a field in the in plane direction, there is it shows only one peak, there is a characteristic transition temperature. But when you do the AC susceptibility with field out of plane, you see there is a small bump is coming here. And you look at the susceptibility versus temperature, there was only one peak. As you are increasing the field, so it is coming two peaks, and when you go to very high field, so it is again one peak. That means it tells that there is some magnetic transformation. There are many states, and as you apply the field, the magnetic state evolves as a function of a magnetic field. And if you look at the bromine sample, it is much more interesting. You look at the H parallel to B, and this is a zoom in view of here. You see beside your main transition, what is typically you see a peak, but there are two other transitions here. You see kind of peaks, but you see along out of plane direction, you do not see because there is nothing here. And similarly, you see here, it is not only one peak. As you increase the magnetic field, because with magnetic field, the phase evolves, whatever the ground state, that now evolves. So you see from one peak to two peak, then it goes to three peak like this. And when you apply more field, because all the spins are aligned in the direction of field, you get a polarized ferromagnet. When you apply more field, then you get only one peak. So based on a detailed things, we proposed this phase kind of phase diagram, where for the chlorine case, we see a connected structure to a polarized, fully polarized ferromagnet. For a bromine case, we go from a conical spin spiral, because we see there are two peaks in the AC susceptibility, from a conical spin spiral with some period to another period, that is your second, then we get to A2C UBO4. When doing this work, we came to know this work from a Japanese group, and they show that the spin-orbit interaction in this material, they did similar kind of work. The spin-orbit interaction in this kind of material can completely change, though we are thinking that it is a completely ferromagnet, but it can have a decanted structure, and when I apply field, it will go to a field polarized ferromagnet. But this was not goal. In 1 second I will finish. Our goal was to, because I showed you in the first slide, there are many two-dimensional magnetism people have seen, but those are kind of in large spins, like chromium and other spins. What my goal was to start with this project is, can we really stabilize a 2D magnetism in a copper-based system? Because that is a quantum spin, you have one mu b. So this is the work going on. So far Pujalin is here, we have not been able to really make it one monolayer. So we are kind of 3 layers now at this moment. So we really want to go one monolayer and see, because of it is one mu b. So far there is no 2D magnetism considering one mu b, and we want to see if there is violation of Mermin-Wagner theorem or not. So that was what is our goal. Thank you very much.
Questions?
It is, I mean, one day or 2 days maximum.
Dependence the temperature dependence of the spin orbit coupling. It is reflected in the resistivity or the low temperature.
I mean, you were talking about first part of the talk?
Yeah.
Spin orbit coupling reflecting means?
So the temperature dependence of the spin orbit coupling you mentioned.
Yeah, I think that's what we did, plot it. Where is that? BSO versus temperature, we have plotted it here. Because I told this is inversion symmetry. If you have there is a breaking, then you could go to DP mechanism. There are two mechanisms. So depending upon your.
Are there any other sources of temperature dependence anything related to the phonons or the lattice? Is there any? My question is there any other model?
Is there any other relaxation mechanism beyond these two? Could be, but I don't know.
This system.
Yeah. Any other questions? Anyone?
The second part of examples, they do show magnetoelectric coupling at
Which one?
the copper complexes.
Yeah, there have been, they show some magnetoelectric and multiferroicity. This copper-based system, they show this kind of things.
Okay, thanks.
Any other questions? Anyone? Yeah. If not, I have a question.
Yeah.
So I didn't get at the last that why the TC is higher. So
Yeah. So what I told, when we are putting bromine,
Yeah.
the copper distance is increasing. So naively one should expect that TC. But what we are telling is that the overlap, the orbital overlap, because bromine is bigger ion, though copper distance is large, but the differential overlap is more. So that is why we are getting large TC.
Okay. Yeah. If no more questions, let us thanks Debakanta for nice talk.